Hi! Today we will have a look at the arguably most complex feature of C++20, coroutines. I should warn you though, the support that C++20 brought us is targeted mainly at library implementers. Coroutines are simply functions with at least one of the co-return, co-yield, or co-wait keywords in their body. The compiler will then generate a framework of code around this function that relies on user-defined return and promise types. These types are the main chunk of code that you will need to write yourself, at least until C++23 brings us a support library. Let's start with the simplest coroutine that you can currently write. A coroutine that does nothing and immediately returns. To turn a function into a coroutine, we need to use the coroutine keyword. The return type task is what we need to write ourselves. And it must contain a member type named promise type, which conforms to the requirements of the compiler. One way to indirectly observe the generated code is to instrument these methods with debug prints. There are a few hidden things here, so let's go through it. Not seen in the output, the coroutine state is allocated on the heap. Then, an instance of the promise type is constructed. We can see the call to the constructor in the output. Next, the getReturnObject method is called, and the result is kept as a local variable. The call to this method and the constructor of task is visible in the output. Just before entering the coroutine body, the generated code will invoke co-wait on the result of initial suspend. We will talk about co-wait and awaitable types later, but here the result is straightforward. When we use co-wait on an instance of standard suspend never, the execution will simply immediately continue. Since the coroutine wasn't suspended, we continue into the coroutine body, which only contains a co-return. Hitting the co-return will result in a call to return void. If you are returning a value, the method would be return value. After exiting the body, the generated code will again evoke co-wait call, this time on the result of final suspend. As with initial suspend, we are returning standard suspend never here, causing the execution to continue. At this point, the coroutine is finished, the promise is destroyed, and the state is deallocated. Finally, as the control returns to the caller, the result of getReturnObject is returned to the main function. When the main goes out of scope, the return object is also destroyed. I haven't talked about one of the method, unhandled exception. As you might expect, this method gets called when there is an unhandled exception during the coroutine execution. What exactly you want to put here depends on your application. For my use cases, I will be relying on standard terminate. So far, the coroutine behaved exactly like a function. So let's do a small experiment and change the result of initial suspend to suspend always. This means that before entering the body, the generated code will invoke co-wait on an instance of suspend always. The result of which is that the coroutine is suspended and the control returns to the caller. So let's look at the output of the instrumented code again. We are leaking the coroutine. We know this because there is no call to the promise type destructor in the output. So what happened? Well, as I said, the coroutine will be suspended just before entering its body. This is not a problem by itself, however, when the control returns to main, we have no means of resuming this coroutine. To resume a coroutine, we need access to its handle. We can use the getReturnObject method to access the handle and then pass it to the task class. We can also add a bit more code to the destructor to prevent the coroutine from leaking if we don't resume it. Note that calling destroy on a coroutine that isn't suspended is undefined behavior. To finish the work here, we also should make our task type move only, since we only want one caller to have access to the coroutine at a time. With this, we can now resume the coroutine and have it finish naturally. If we don't, it will be destroyed in the destructor of task when we exit the scope of main. So far, we have spent all time fiddling with a coroutine that did nothing. So let's have a look at an example of a coroutine that is actually useful. A simple generator. Most of the code is the same, so let's step through what changed. First, we switch the co-return to co-yield inside of our coroutine. Similar to co-return, the generated code will expect a corresponding yield value method in the promise type. In addition, however, it will invoke co-wait on the result of this method, allowing us to suspend the coroutine after a value is generated. Here, we return an instance of suspend always, which means the coroutine will be suspended after each generated value. We have also introduced a getNext method. This method will resume the coroutine. In turn, the coroutine will generate a value and suspend itself by returning suspend always. And we then return this generated value. The getNext interface is a bit awkward to use, but you can easily extend this idea by turning it into a range, like this example on CPP reference. So far we have used suspend always and suspend never. Let's have a look at how you can write your own awaitable types. An awaitable type must have three methods: await ready, await suspend, and await resume. Await suspend can have one of three variants: returning a void, returning a boolean, or returning a coroutine handle. Let's start with await ready and await resume. Await ready is essentially a shortcut. If this method returns true, we skip the suspension and continue to await resume, which is always called immediately after the coroutine is resumed. This will be useful for cases when we await on the availability of a resource, however the resource is already available. Let's talk about await suspend. Very importantly, the coroutine is suspended before entering the body of await suspend. This means that the coroutine can be treated as data, for example passed between threads. The void version will simply return control to the caller. The same for returning true in the case of the boolean variant. If we return false, the coroutine is resumed instead. Note that this differs from returning true in await ready, since in that case the coroutine is never suspended. The third version is the most complex, returning a coroutine handle. The generated code will then resume this handle. This is important behavior for chaining coroutines. If we would simply resume the handle ourselves inside of await suspend, we would be growing the stack. This does not happen if we let the control return to the generated code first. A good rule of thumb is if you are resuming a coroutine handle directly in your await suspend, consider using this version instead. Finally, let's have a look at an example of an awaitable. Note though that using this awaitable would be pretty pointless. In the await suspend, we launch a new thread that will sleep for the desired duration and then resume our coroutine. Note that this is safe simply because the coroutine is already suspended before entering the await suspend body. This in turn means that the suspension happens before relation with the start of the new thread. Also note that we are indeed moving the coroutine between threads. And that is all I have for you today. If you still have questions, follow me on social media where you will find additional examples. Also subscribe if you want to catch the follow-up video on the C++ 23 coroutine support library. Thank you for watching and see you in the next one.